Hi students, today we will learn two-group CC disconnection. In that we'll learn synthesis of 1,5-difunctionalized compounds. So 1,5-difunctionalized compounds means it is similar to 1,3-difunctionalized compounds, but here the two functional groups will be at a position of 1 and 5 to each other. So these also come under the CC disconnection. Now let us look at some example. See, the two functional groups will be in 1,5 relationship between each other. Bond between third and fourth carbon is usually cleaved. So now let us look at the general mechanism. So here I have written the first equation here. So usually the bond between 3 and 4 is usually disconnected, but it is not the case in all the examples. But looking at the target molecule, we can do the disconnection. Sometimes there is disconnection between 2 and 3 carbon atoms as well. So it is going to give rise to synthons and then further synthetic equivalents. Now let us take the example target molecule 1. So here you can first start numbering the carbon atoms. So if you start numbering the carbon atoms, we will know that if you start numbering from the hydroxyl group, that is a carbon atom attached to the hydroxyl, 1, 2, 3, 4, and 5. So it is nothing but 1, 5 difunctionalized. So the two carbonyl groups are at a position of 1, 5 to each other, 1 and 5 to each other. So hence we're going to write the retrosynthetic arrow, and above that we will mention as 1, 5 DICO. Means DICO stands for disconnection of the carbonyl. So CO. So 1,5C diCO, and then we will be writing down the synthons. Now the cyclohexanone is going to, once you cleave the cyclohexanone ring, once you cleave the bond between cyclohexanone and the adjacent carbon, we are going to get a positive charge on the cyclohexanone, and the subsequent synthon would be a cation. Now the synthon for the cationic cyclohexanone would be a alpha beta unsaturated compound. There is nothing but cyclohexanone is going to be the synthetic equivalent for the cationic synthon, because you can remove the proton from the adjacent carbon atom, which is going to give rise to the double bond. So the synthetic equivalent is going to be cyclohexanone. And coming to the cationic synthons, here we have already studied in the previous slides that whenever you have a carboxylic acid or an intermediate of this kind, a cationic synthon for a carboxylic acid, then you can always make use of the ethyl ester as the fragment. That is, you can attach the ethyl ester to the synthon, because the COOET is a very good group whenever the reaction involves alkylation of ketone. So for alkylation of ketone, we can always make use of COOET, ethyl ester, we can use it as a fragment for the attach it to the synthon, so that we are going to get a synthetic equivalent of this kind, so that it was very much easier for the synthesis. So now when you look at the synthesis, we have a proton, that is the acidic proton, which is attached to the ester group. So first that is going to be removed by the base. So that is OET minus is going to remove the proton from the base. Now there is going to be a nucleophile. Now this nucleophile is going to attack the cyclohexanone, that is nothing but alpha beta unsaturated group, alpha beta unsaturated compound, and it is going to give rise to nothing but the alkylation reaction. That is, there is going to be bond formed between the ester and the cyclohexanone. Now the last step would be reaction with potassium hydroxide. This is nothing but an aqueous potassium hydroxide, usually is used for the hydrolysis process. So once it is used, then what happens is there's going to be the cleavage of the ethyl ester that's going to get cleaved, and you're going to get the target molecule. So all these 1,5 difunctionalized compounds are examples of Michael reaction, because when you look at the synthesis, Michael reaction is nothing but Michael reaction is also called as Michael addition, and it is nothing but the nucleophilic addition of a carb anion or another nucleophile to an alpha beta unsaturated carbonyl compound. So now here you can see that's the nucleophile, and it is going to attack another alpha beta unsaturated compound. So hence all these kinds of examples are nothing but Michael reaction. So whenever you come across a target molecule which is wherein there is 1,5 difunctionalized group, then you can always make use of Michael reaction, and you can write down the synthesis. So this is how you're going to get the target molecule 1. Now let us look at another example. This is also similar example. So here, once you start numbering, you're going to find that the 2 carbonyl groups are 1 and 5 positions from each other. And hence we can do the 1, 5 disconnection of the carbonyl. So here, you're going to do the disconnection between 3 and 4 carbon atom. And we're going to be getting 2 synthons, cationic and anionic synthons. Now, the synthetic equivalents also we can write down. See, now, whenever you have a carbonyl group and there is a possibility of writing down an alpha beta unsaturated, then please go ahead for as writing down as a synthetic equivalent, because we can do the further functional group interconversion. See, whenever you have the synthon of this kind, that is a carbonyl group which is attached to a ethyl group bearing a positive charge, then you can make use of writing the synthetic equivalent as an alpha beta unsaturated. That is a hydrogen from the adjacent carbon of the carbonyl carbon proton is abstracted, and then we are going to get a double bond. So now you can see that this is nothing but an alpha beta unsaturated compound. Now we can do easily we can do the functional group interconversion. In the 1,3 difunctionalized compounds, we had studied that alpha beta unsaturated compounds can be converted to the beta hydroxyketone. That is what we had studied in some of the examples in 1,3 difunctionalized compounds. So here also we are going to make use of the same reaction here. Same mechanism we are going to make use, and that is we are going to write down the functional group interconversion of the alpha beta unsaturated compound and going to write down the beta hydroxyketone. That means that beta hydroxyketone is nothing but once there is the removal of the hydroxyl group, again it is going to give back the double bond, as the alkene. Conjugated group is going to be brought back. So hence there's nothing but you can easily do the functional group interconversion to the beta hydroxyketone. Now once you have a beta hydroxyketone, now you can, if you start numbering, you're going to see that this is an example for the 1,3 difunctionalized compounds. So hence we will be doing the 1,3 disconnection. So you start numbering see, ketone group always gets the highest numbering. So ketone is 1, adjacent carbon is 2, and the carbon bearing the hydroxy is going to be 3. So hence we are going to do the 1,3 disconnection. Once you do the 1,3 disconnection, you can see that it is going to give rise to 2 synthons. The ketonic group is going to get the anion, and the alcohol is going to get the positive charge. So this we can also, you know this how to give the signs, because the carbon is going to get a positive charge, and the adjacent carbon, that is carbon 2, is going to get a negative charge. That is what has been written here as a synthon. Now when you come to the other synthon, then the carbon bearing the hydroxyl group is going to get a positive charge, because oxygen is highly electronegative, and hence carbon which is attached to oxygen is going to get a positive charge. Once you write down the synthons, the next step is going to be writing down the synthetic equivalents. Now the synthetic equivalent for the anion is nothing but there's going to be a proton abstraction, and you're going to get an carbonyl group. That is the formaldehyde you're going to get. Sorry, you're going to get acetone, CH3. You're going to get acetone. And coming to the cationic synthon, you're going to replace it. That is, the hydroxyl proton is going to be removed. Okay, then what is happening is oxygen is going to get a lone pair on it, extra electron pair on it, and it is going to form a double bond between the carbon and oxygen to give a formaldehyde. So this is how you're going to get. So these two are going to be the synthetic equivalents. Now you can make use of this synthetic equivalents, and you can you can synthesize the target molecule 2. Now let us see how it is to be done. Now first step is always we have to use these 2 synthetic equivalents, that is the starting materials, and get the alpha beta unsaturated compound. So that is what the first step we are going to do. So one by one we are going to take the separate compounds, and then we will analyze and we'll do the synthesis. Now first we have the formaldehyde. Now here what is going to happen is a proton is going to abstract the, oxygen is going to abstract the proton. It's going to give a positive charge on the oxygen in this format. So this is going to be the first starting material. Now the second starting material is what we have is nothing but the acetone. Now this is what we are going to write down in the enol form. Ketoenol form we are going to write down. Now at this point we are going to react this ketoenol form to the starting material 1. So once you react with this, what is going to happen is there's going to be the movement of the electrons. There is nothing but oxygen is having an extra lone pair. It is going to form a double bond between carbon and oxygen to give a ketone carbonyl group, and the double bond alkene group is going to attack the carbon is going to attack the carbon which is having attached to the hydroxyl group, since carbon is more electropositive, and the movement of electrons between carbon and oxygen moves towards oxygen to give a negative charge. There's nothing but this intermediate. Okay, so this can also be written as this one. There's nothing but we're just flipping the carbon atoms. Now at this point we are going to do the condensation. Condensation is the hydroxyl group of the carbon atom, one carbon atom, and the hydrogen of the adjacent carbon atom is going to be removed, and there's going to be the formation of a double bond. Now here we have the formation of the alpha beta unsaturated compound. Now this alpha, that is, we have the alpha beta unsaturated compound. Now this is going to react with the ketonic group. Now the next step would be we have the carbonyl group. Again we have the alpha carbon and the proton, which is highly acidic. Hence we can easily abstract the proton using a mild base minus ETO minus, and we're going to get a nucleophile. Now this nucleophile is going to attack the conjugated diene, that is nothing but the alpha beta unsaturated compound, and there is going to be the movement of electrons from alkene towards the carbon to give a complex of this kind. It's going to give a compound of this form wherein there is a negative charge. Now what is happening, the last step would be the proton is going to be abstracted. The negative nucleophile is going to abstract the proton, and we are going to get the target molecule 2. So this is how you can do the synthesis. It is very simple. Only thing is that you have to constantly just note the movement of electrons. Once you start writing the movement of electrons and once you practice well, it is going to be very, very easy. Because now in retrosynthesis, all the target molecules are easily distinguishable. It is not that there is any kind of confusion. Once you start solving more and more problems, you can easily know what is CC disconnection, what is 1, 2 CX disconnection, what is diel-Sandler reaction. So all these can never be confusing if you practice well. So this is a very easy chapter. So just solve more and more problems. Next, we have target molecule 3. So here what we have is, again, you see there is the ketone group and there is the acid group here. And once you start numbering, the numbering starts from the carboxylic acid, 1, 2, 3, 4, and 5. Ketone gets the numbering 5. So hence it is 1, 5 difunction compound. Now this can again be, we can use the 1, 5 disconnection. We are going to write down 1, 5 DiCO above the retrosynthetic arrow. This is going to give rise to 2 synthons. It's going to give rise to 2 synthetic equivalents. One is nothing but the cyclohexenone, and the second is nothing but the malonic group. So here what happens is, see here we can interchange, we can convert the CH2COOH minus in this form, because we know already that wherever there is an ethyl ester group, then it is always very much easier to use it in the synthesis, because it is going to be unreactive, and it is a fast reaction also, which can be used for the alkylation of the ketones. Now the corresponding synthesis, it is going to be we are going to follow the same synthesis as the previous example, and here we have to use KOH. Wherever there is hydrolysis, please use aqueous, write down as aqueous KOH, because it is a good reagent for wherever there is the hydrolysis to be performed. And then we are going to get the target molecule. It has the same synthesis as the previous examples. The next topic we'll go for Robinson annihilation. Robinson annihilation is a very good synthesis in organic chemistry, because it always helps in the ring formation. Wherever there's a ring formation, then we can make use of Robinson annihilation. So now here, this is an extension of Michael reaction to make 6-membered rings. At first, we might think of a diels-Alder disconnection of 61 as it is a cyclohexene with carbonyl groups, but it's a wrong disconnection. Disconnection at alpha-beta double bond, however, reveals a simple 1, 5 disconnection, that is 62. So whenever you have a cyclic ring structure with an alpha-beta unsaturated compound in it, alpha-beta unsaturated compound as a target molecule, then you can usually disconnect the double bond and you can give, and it can be written as, once you disconnect the double bond, it is going to be, the intermediate is going to have a 1,5 difunctionalized compound. Now, from this, you can do the move on from the with the 1,5 dico disconnection, and then you can do the synthesis. So now here, first step would be disconnecting the double bond. Once you disconnect, that is alpha beta double bond, and you're going to write down as alpha comma beta above the retrosynthetic arrow. You're going to give, it is going to give rise to a diketone group like this, because whenever there's a double bond, you do the disconnection, it is going to give a ketone group. Because again, when you try to do the ring synthesis, it is nothing but a condensation. Again, you do the reaction, then you are going to get back the double bond. That is, you're going to get back the ring. So hence, we are going to make use of, so once the disconnection takes place of alkene, it is nothing but a ketone, that is, we are going to write down. That's a diketone is going to be obtained at 62. Now here, when you start counting you start numbering the carbon atoms, right, you can see that you're going to get 1, 2, 3, 4, 5. That is nothing but a 1, 5. It is nothing but 1, 5 difunctionalized compound. Now from here, you can follow the same steps. It is nothing but you can do the 1, 5 dico disconnection, and you're going to write down the synthons and the synthetic equivalents. See, the synthetic equivalents, once you do the disconnection, right, you're going to get a negative charge on the ethyl ester, and it is nothing but, it is the negative charge can be removed when a proton is being abstracted. And for the other synthon, that is a cationic synthon, it is going to be a double bond. There's going to be a double bond next to the phenyl group, and that can be removed when there is abstraction of proton and you're writing down the double bond. So these two are the synthetic equivalents, and then we can make use of the writing down the synthesis. So here, Robinson annihilation comes into existence is because you have the two starting materials, and with ETO minus, you're going to get a compound of this kind as a diketone. Now the next step would be you're going to do the reaction condensation, wherein we are going to remove the ketone group, and you're going to get a double bond. So this is how you're going to make use of the Robinson's annihilation. So this gives rise to this is nothing but the cyclization reaction and the ring formation, which is the Robinson annihilation reaction. So we have some more examples. A cyclic ketone is converted into another cyclic ketone with a fused pair of 6-membered rings containing a double bond in essentially one step. So here also we have a bicyclic compound here, and you're going to do the same disconnection at the double bond. It's going to give rise to a diketone, and then we're going to disconnect it further. That is, we're going to make use of 1,5 disconnection. That's why we're writing as 1,5 dico. Once you do the 1,5 dico, you're going to disconnect. If you start numbering, right, that is, if you start numbering of this compound, it is 1, 2, 3, 4, 5, 1,5 disconnection. And you can make use of disconnection just next to the, cyclohexanone. We are going to get the two synthetic equivalents of this kind, of this form. So here what happens, the cyclohexanone is going to bear a negative charge, and the synthetic equivalent is nothing but protonation, and you're going to get the cyclohexanone structure, diketone structure. And for the other synthon, it's that is the carbonyl group is going to have the positive charge. Now how you can remove the positive charge is when there is a deprotonation, you're going to get a double bond. So that is how you're going to that's how the generation of the alpha beta unsaturated compound is possible. So this is these two are the synthetic equivalents. Now the synthesis would be, again we're going to make use of the KOH, and then we are going to react in presence of MEOH, that is methanol, we are going to react it, and we are going to get the target molecule 63. So this is how we can do the synthesis for the 1,5 difunctionalized compounds. So this ends this chapter. Thank you very much.